Artificial intelligence is everywhere, powering incredible new tools and insights. But these AI models, especially the really big ones like large language models, are incredibly hungry for computing power. They're pushing our current computer chips, the silicon-based ones we've relied on for decades, to their absolute limits. You've probably heard of Moore's Law, the idea that chip power doubles roughly every 2 years, while that engine of progress is slowing down. It's getting harder and more expensive to keep making transistors smaller and faster. Plus, there's another big problem. Just moving data around inside a computer, between the memory and the processor, eats up a huge amount of time and energy, sometimes more than the actual calculation. So, what's the answer? Researchers are exploring exciting new avenues, and one of the most promising is photonic computing. Instead of using electricity and electrons, photonic processors use light, photons, to perform calculations. Think of it like computing at the speed of light, literally. Why is light so good for this? Well, light travels incredibly fast with very little resistance, which means photonic systems can potentially offer much higher speeds or bandwidth and lower delays or latency compared to electronics. They also generate less heat, leading to potentially massive gains in energy efficiency. This is crucial as AI's energy demands are soaring. Photonics is also naturally suited for doing many calculations at once. Imagine encoding different streams of data onto different colors of light and processing them all simultaneously. That's a technique called wavelength division multiplexing, and it's a huge advantage for parallel tasks common in AI. We're not just talking theory anymore. Companies and labs are building actual photonic chips, sometimes called photonic integrated circuits or optical neural networks. These chips have already been shown, running demanding AI models you might have heard of, like ResNet for image recognition or BERT for understanding language, without needing the models to be changed. Some recent photonic processors are achieving mind-boggling speeds. One system hit over 65 trillion operations per second using a special data format, all while being relatively power efficient. And importantly, the accuracy of these light-based calculations is getting very close to the standard 32-bit precision we expect from digital computers, thanks to clever design and specialized number formats that handle the analog nature of light. Much of this is being built using silicon photonics, which is great because it potentially integrates with existing chip manufacturing processes. Researchers are also looking at other materials that might offer even better performance. Often, these are hybrid designs. The core calculations, especially things like matrix multiplications, which are fundamental to AI, are done with light, while electronic components handle control and communication. This lets computations happen extremely fast, sometimes in less than half a nanosecond, and dramatically cuts down the energy wasted moving data around. Now, it's not all smooth sailing yet. Working with light in an analog way makes achieving high precision consistently a challenge due to noise. Building these complex chips reliably and affordably at a massive scale is another hurdle. Integrating them smoothly with our current electronic systems, managing heat, developing the right software tools and algorithms, these are all areas needing more innovation. So, what's the future look like? Photonic processors probably won't replace your standard CPU or GPU overnight. Instead, expect them to first appear as specialized accelerators, working alongside traditional chips to handle the most demanding AI tasks, particularly where energy efficiency and data movement are critical bottlenecks. Think of how GPUs started for graphics and then became essential for AI. Photonics could follow a similar path. By tackling the energy and data challenges head-on, photonic computing offers a really exciting route to keep AI advancing, leading to more powerful and sustainable AI systems in data centers, and maybe even extending to devices closer to us. It's a key step towards the next generation of computing, beyond the limits of traditional silicon.